So we have here a series of reinforced concrete beams spaced at 2.4 meters on centers and have a simply supported span of 4.6 meters. So meron tayo ditong floor plan. Ito, may floor plan tayo dito. Pag tinignan mo daw yung section ng floor, it will look something like this. So it is composed of several T-beams. Kung tutusin, T-beams sila yan. Yung mismong floor being supported by reinforced concrete beams na reinforced sa tension side lang. So nasa tension side lang yung reinforcement ng mga beam natin. Ang spacing daw, center to center spacing ng mga beam ay 2.4 meters as was mentioned sa problem. Center to center spacing nila 2.4 meters, and then yung mismong length nung mismong beam na simple supported daw ay 4.6 meters ito. So center to center din yun as given in the problem. The beam support a reinforced concrete floor slab 100 mm thick. So yung thickness daw ng slab natin that is being supported by the beams ay 100 mm. The dimensions and reinforcement of the beam are shown in the figure. As you can see here, ang mga beam natin reinforced with three bars, and then yung distance from the bottom of the slab papunta dun sa centroid ng mga reinforcement ay 300 mm. And then yung width ng mga beam 250 mm. And then according dito sa problem, ang diameter daw ng mga bars ay 25 mm. Ang FC prime ng concrete 20.7, and then ang FY ng steel 414 megapascal. And with that, given all of those information, the question asks for the design moment strength of a typical interior beam. So we will be investigating the design moment strength of an interior beam. So parang ito. When we say interior beam, beam siya na nasa loob. Kasi merong edge beam or yung exterior beam, meron ding interior beam. So interior beam yung pinapa-analyze natin dito. Similar to this. So ito yung i-analyze natin yung T-beam na to. Okay? So with that, let's start. Let's start to find the design moment of this given figure. Okay? So before we proceed with the solution, first things first, we have to know kung ano yung effective flange width ng T-beam natin. Usually, nangyayari ang T-beam for monolithic construction kapag binubuhusan yung concrete beam together with the slab. And usually, in practice, ganoon naman talaga yung nangyayari. Pag yung beam binuhusan, usually sabay yung slab para monolithic sila. Pag monolithic mo binuhusan yung concrete beam together with the slab, usually that will act as a T-beam. They will act as a whole section. Parang isang section na lang sila. They will not act as two separate elements na slab tapos beam. No, they will not act like that. They will act as one beam, which is what we call that as a T-beam. Okay, pag binuhusan mo na sila monolithically. So first things first, we have to know the effective flange first. Effective flange width. So compute muna natin yung effective flange width. And how do we know? How will we know yung effective flange width? We can refer dito sa code, sa T-beam geometry. So pasok naman tayo dito sa sa first row dito nung nasa table. So sabi niya dyan, yung effective flange width, which is BF, I'll just use BE na lang. I'll just use the notation natin dito sa discussion para ano lang tayo, consistent lang. But you have to remember sa code, yung effective flange width is designated as BF, and then yung thickness IH sa code. Pero dito, tawagin na lang natin yung thickness as T, tapos yung effective flange width as simply B, or BE, I mean. Okay, so according to the code, ang effective flange width daw is yung width ng web, BW, plus the list of this. List of 8H, SW over 2, tsaka sa LN over 8. For those T-beams na may flange on each side of the web. So ito yung web natin. So may flange siya on each side, itong dalawa. So therefore, pasok tayo dun sa unang row dito sa table. Okay? So, diretso ko na lang na isolve dito sa problem natin yung effective flange width niya. considering yung first requirement dito. So sabi natin, yung effective flange width is yung width ng web, which is 250 mm, as was mentioned in the problem, plus yung effective overhanging flange na to, which is 8 times h daw. Wherein yung h mo ay yung thickness. So this is your h, this is your BW. Lagyan lang natin ng notation. Yan. 8 times thickness na 100. But you have to take note, yung 8h na yon, that is on each side of the web. On each side of the web dapat yun. Okay? So since dalawa yung side ng web, edi times 2 natin to. Times 2 natin yan. Okay? So therefore, ang lalabas dyan will be 250 plus 8 times 100 times 2. So that will be 1850 mm. 1850 mm. Okay? But we also have to check yung other two formulas pa to know kung ano talaga yung magiging effective width or effective flange width. So check din natin yung two other formulas. Effective flange width will be equal to BW, which is 250, plus neto, SW over 2, wherein yung SW ay yung clear distance between the edge of the web papunta dun sa edge nung kasunod na web niya. So according dito sa problem, given na 2.15 or 2,150. So that will just be equal to 2,150 divided by 2. As was mentioned dito sa code, SW over 2. Since dalawa sila on each side, times 2 na lang natin yan. So makakancel na lang yung 2. Okay? So compute natin kung anong lalabas dyan. That will be the second option for the effective flange width. And then check din na rin natin yung last, yung ln over 8. So that will be BW plus ln over 8, wherein supposedly yung ln, that is the clear distance dapat from the, yung clear length dapat yan ng beam natin. So dapat yan from this edge of the column hanggang dito sa edge ng column natin sa kabila. Okay? Kaso lang medyo wala namang given na dimension ng column. So we don't have any choice. Gamitin na lang natin yung center to center spacing. Okay, yung 4.6 na given. So that will be 4.6 or 4,600. 4,600 divided by 8 times 2. Kasi on each side. On each side of the web dapat. So that will be 250 plus 4,600 over 8 times 2, which will be equal to 1,400. Okay? So alin sa kanila yung pipiliin natin? Ang hinahanap dito yung list of. Okay? So kahit naman i-minus mo yung 250 sa lahat ng to, madali mo naman malaman kung ano yung list sa kanila, which is this, yung 1,400. So yan yung nag-govern or nag-govern dito sa effective flange width natin. Since siya yung naging pinakamaliit. So with that, therefore, we can say na yung effective flange width nitong given natin na beam, for example, itong flange natin na to, or itong T-beam na to, we are assuming na yung effective flange width niya is just 1,400. So, assuming na ito yung 1,400, kunyari. Yan. 1,400 mm. So, hanggang dito lang yung i-consider natin, ibig sabihin. Yan. Hanggang dyan lang na flange width. Okay? So, that will be our effective flange width B. Okay? So, after knowing that, it's now time to know which case will this T-beam will fall. Okay? So, check natin. Check muna natin. Pag nag-analyze ka ng T-beam, ang pinaka basic step to know whether you need to analyze it as a singly reinforced or doubly reinforced or T-beam analysis. You just have to check if yung depth of compression block is less than or equal to the thickness. Okay? So, paano natin malalaman if the the depth of the compression block is less than or equal to the thickness. We can just assume na yung T-beam natin nagpo-fall sa case 1, which is ito nga, yung case 1 na to. Okay, so paano ba itsura nung case 1 na yan ulit? Kung ito yung T-beam natin, if this is our T-beam, yan, may web siya dyan, we are assuming na yung stress distribution or yung depth ng compression block dyan sa T-beam natin ay less than or equal sa thickness. So, ito lang, hanggang dyan lang yung depth ng compression block. Yan lang yung A natin. Which is being balanced by the force acting dito sa tensile reinforcement, which is this, yung T. So, yung resultant ng compression block natin, we call that as yung C. Simply call that as C. Itong resultant na to. With a depth equal to A. A yung depth niyan. Tapos ito yung thickness natin, which is yung T. Tuwagin na lang natin siya na T para consistent. And then yung effective flange width dito. Effective flange width natin will be yung BE. BE yung magiging effective flange width natin. Yan. So, this is our BE. Ito yung A. Okay? So, from that assumption that yung depth of compression block is less than or equal to the thickness, we can just utilize yung equation of equilibrium from the singly reinforced beam, wherein yung C is equal to T. Okay? So, yung C natin, assuming na 0.85 FC prime yung magnitude ng stress dito. So, that will just be equal to, parang sa singly lang, 0.85 FC prime AB, wherein yung B natin is supposedly yung BE na. Kasi ito na yung yung nakakaramdam ng compression dyan eh. So, yung area natin dyan will now be A, which is yung depth, times BE na. So, lagyan ko na ito ng subscript na E. So, that must be balanced by tension force, which is will be coming from the tensile reinforcement SAS multiplied by Fy, assuming that tensile steel yielded. Okay? So, take note, ang tamang equation dyan is supposedly Fs. ASFS dapat. Yun ang tamang equation dito. ASFS. But then again, since we are assuming that this is a properly designed beam, wherein dapat yung tensile reinforcement niya ay nag-yield. So, we will just assume na yung Fs natin is just equal to Fy, showing na yung tension reinforcement nag-yield. Okay, so from there, we just have to substitute corresponding values, 0.85 times FC prime, which is 20.7, 20.7 times A, which is unknown. BE natin, yung 1.4, pinakamaliit. And that must be balanced by AS na tatlo. Tama, tatlo. Tatlong diameter 25. Diameter 25 mm squared. Okay, that will be our AS, and then yung Fy natin ay 414. Okay, so solve na lang natin yung A dyan. A is just equal to 3 times pi over 4 times 25 squared times 414 over 0.85 FC prime AB. So, ang A natin dyan will be 24.75. 24.75 mm. Which is definitely less than the thickness of the flange. So, obviously, with that, we can assume na yung T-beam natin is not actually a T-beam. I mean, hindi siya nagre-require na i-analyze natin siya as T-beam. But, pwede natin siyang i-analyze as parang lang, singly reinforced beam lang. Okay? That is obviously less than T, which is equal to 100 mm. So, therefore, confirm analyze as singly reinforced or SRB na lang. Para shortcut na lang. Tawagin ko na lang siya na SRB. Analyze as SRB or singly reinforced beam. Analyze as SRB. Okay? So, yun. Pwede na natin siyang i-analyze as simpleng ano na lang, singly reinforced beam. Okay? So, before we proceed with the computation of the uh, moment capacity, kasi yun naman yung hinahanap sa problem. Before we proceed with that, we can conduct checking muna or verification. Like, check muna natin yung ano, yung raw min niya. Check muna natin kung pasok siya doon sa minimum raw min allowed by the code. So, we can just check, mabilisan lang, check raw min. Check raw min. So, ang raw min natin will be most probably, since ang FC prime natin 20.7, most probably ito mag-govern dyan. 1.4 over Fy. 1.4 over Fy na 414. So, that will be equal to 1.4 over Fy na 414. 0.00338. 338. So, compare na natin yan sa rho actual. Rho actual is just equal to AS over BD. Ang AS natin ay 3 pi over 4 diameter squared. Divided by B na 250 times D. Take note, ang D natin is actually 300 plus 100. Kasi ang D natin dapat mula dito sa centroid ng tensile reinforcement hanggang dito sa top dapat. Yan ang D natin. Okay? So, ang D natin will be 300 plus 100 or 400. Okay? So, check natin kung ano yan. 3 times pi over 4 diameter squared over 250 times 400. So, it will be 0.01473. Tama? 0.01473. Which is definitely greater than rho min. Therefore, okay. Ilan naman yun? Gusto lang natin malaman kung okay ba siya, kung greater than ba siya sa rho min or hindi. Okay? Next thing that we have to do is verify natin yung mga assumption natin. Or isa lang naman yung inassume natin eh. Inassume lang natin nung una na tension still yielded. So, verify lang natin kung talaga nag-yield siya. That is the next thing that we have to do before we proceed with the computation of the moment capacity. Verify assumptions. Verify lang natin yung assumptions natin. So, check lang natin yung tensile strain niya. Formula sa tensile strain, alam na natin yan. 0.003 times dt. Yun yung tamang formula. dt dapat yun, hindi lang siya basta t. dt minus c over c. Although dito, since single layer lang naman yung tension reinforcement natin, edi dt is just equal to d. Substitute lang, 0.003 times dt na d lang din, which is 400, minus c. Di pa natin na-compute yung c. So, before we will be able to compute for c, we have to know first yung beta 1 natin. And since yung FC prime natin 20.7 lang, pasok siya dito. So, therefore, ang beta 1 natin ay 0.85. Okay. So, with that, we can directly solve for C. C is just equal to, since we know that A is equal to beta 1C. So, compute na lang natin directly yung C sa calcu. C will just be equal to A, 24.75 divided by beta 1 na 0.85. So, that will be 29.12 mm. Okay. So, substitute na lang natin dito, 29.12 over 29.12. So, what will be the tensile strain. 0.003 times 400 minus 29.12 over 29.12. Tensile strain will be 0.03821. 0.03821. Which is, compare muna natin sa yield strain. Check muna natin yung yield strain dito. Yield strain is equal to Fy over Es. Ang Fy natin ay 414. Divide lang natin sa Es na 200,000. So that will be equal to 414 over 200,000, 0.00207. Okay? So that will be our yield strain. So basically, if you will try to compare, yung na-compute natin na tensile strain is definitely, nagkatin ang comment dito, tensile strain, which is equal to 0.03821, is definitely greater than the yield strain, which is equal to 0.00207. Therefore, confirm ulit na tension still yielded. Okay? So, na-confirm natin na yung tension still natin nag-yield talaga. Kasi yung strain niya greater than the strain Y. Okay? So, confirm yung assumption natin. Tama yung ginawa nating solution. And ang maganda pa dyan, since na-compute natin yung tensile strain, if you will try to compare, yung tensile strain natin is also greater than 0.005. And according sa code, kung greater than sa 0.005 yung tensile strain ng concrete section mo, it is tension controlled, therefore ang phi mo ay 0.9. Okay? So therefore, we can say na tension controlled siya. Tension controlled, therefore ang phi natin is just equal to 0.9. Okay, yun yung kagandahan doon kasi na-compute na natin yung tensile strain niya. So with that, I think we can now proceed with the computation of the moment or the design moment strength. Okay, so with that, we can now compute for the moment capacity netong T-section natin. T-section natin na to. Which is just, as we have seen, case 1 lang naman siya. So, yung moment capacity niya will just be the same sa moment capacity on how we computed the moment capacity ng singly reinforced. Okay? So, how do we compute for the moment capacity ng singly reinforced? So, it's just equal to, yung MU natin is just equal to phi times, pwedeng yung C yung gamitin natin, times the moment arm na T minus A over 2. Okay, pwedeng yung compression. Pwedeng compression yung gamitin natin. Wherein yung C natin na nakuha na natin kanina, it's 0.85 FC prime ABE. Okay, wherein yung C natin dyan, ito, is just equal to 0.85 FC prime ABE. Okay, so we can use that formula, or we can use the other term, yung phi times the tension force times the moment arm, which is D minus A over 2 pa rin naman. Okay, wherein yung T natin, napakita na rin natin kanina, yung T natin is just equal to ASFY. So either of the two pwede naman na gamitin to compute for the moment capacity. So siguro I'll just use I'll just use kahit yung ASFY na lang. I'll just use ASFY. So, moment capacity is just equal to AS, or yung phi, which is 0.9, times yung AS, which is 3, times pi over 4, times diameter squared, times Fy na 414, times D na, take note, yung D natin ay 300 plus 100 or 400. 400 minus A, which is, ito, 24.75. 24.75 divided by 2. So that will be equal to 0.9 times 3 times pi over 4 times 25 squared times 414, 400 minus 24.75 over 2. So that will be equal to 212.69 kilonewton meter. So dinerecho ko na siya na kilonewton meter. Okay, so i-box lang natin yan. And we already have our final answer for this particular problem.